Welcome back. In this video, we're going to talk about finite automata, which we'll see in future videos are a good implementation model for regular expressions. So in the last few videos, we've been talking about regular expressions, which we use as the specification language for lexical analysis. And in this video, we're going to start something new. We're going to talk about finite automata, which are are very convenient as an implementation mechanism for regular expressions. And so regular expressions and finite automata are very closely related. It turns out that they can specify exactly the same languages called the regular languages. We won't prove that in this course, but we'll certainly make use of that fact. So moving right along, what is a finite automaton? Well, here's a typical definition as you might see it in a automata theory textbook. Finite automaton consists of an input alphabet, so these are the set of characters that it can read. It has a finite set of states, should probably emphasize that. This is what makes it a finite automaton, is that it has some set of states that it can be in. One of those states is special and is designated as the start state. Some subset of the states are accepting states. So these are the states that, well, we'll define them more in a minute, but intuitively, if the automaton terminates after reading some input in one of these states, then it accepts the input, otherwise it rejects the input. And finally, the automaton has some set of state transitions. That is, if it's in one state, it can read some input and go to another state. So let's look at that in a little more detail. So a transition in a finite automaton, if I'm in this case, I've written out one particular transition. Here, if we're in state 1 and we read the input A, then the automaton can move to state 2. Okay, and there could be lots of different transitions for the automaton from different states and different inputs. And it's read in the following way. If we're in state 1 on input A, we will go to state 2. And if the automaton ends in an accepting state, when it gets to the end of the input, then it's going to do what's called accepting the string, meaning that it will say, yes, that string was in the language of this machine. So intuitively, the automaton starts in the start state, and it repeatedly reads inputs, one input character at a time, makes a transition. So it'll see what kind of transition it can make out of its current state based on that input to another state. And if when it's done reading the input, it's in one of the final states, then it will accept. Otherwise, it's going to reject the input. Now, what are the situations in which it rejects? Well, if it terminates in a state S, that's not one of the final or accepting states. Okay, so if it ends in any other state besides one of the accepting states, then it's going to reject. If the machine gets stuck, meaning it finds itself in a state and there's no transition out of that state on the input. So in particular, let's say that it's in some state S and the input is A and there's no transition. There's no transition specified for state S on input A, so the machine can't move anywhere and it gets stuck, and that's also a rejecting state. And so in these two situations, if either it gets to the end of the input and is not in a final state, or if it never reaches the end of the input because it gets stuck, in both of those cases, it rejects the string. That string is not in the language of the finite automaton. Now, there's an alternative notation for finite automata that I think is more intuitive for examples. And so we're going to emphasize that way of writing them out. In this notation, a state is represented as a node in a graph, which we just draw as a big circle. The start state is represented as a node that has an edge or an arrow into it with no source. So this is a transition into the node, but no source node that it comes from, and that indicates the unique start state. An accepting state is drawn as a node with just double circles like this. And finally, a transition is drawn as an edge between two nodes of the graph. So what this says is if I'm in this state that I'm circling in blue, and I read the input A, well, then I can move to this state that at the tail of the arrow. So now let's do a simple example. Let's try to write out the automaton that accepts only the single digit 1. So we'll need a start state. and we'll probably want an accepting state as well. And now the question is, what do we put in between the two? Well, there'll be some kind of a transition here, and it's a good guess that we should take that transition if the machine reads a 1. And now let me take a moment here to talk about how the machines execute. So let's label these states. Let's call this state A, and let's call this state B. Okay. So the machine will have some input. Okay, and we can write that input out over here. So let's just say we have the single character 1, and it begins in some state, namely the start state. And so one configuration of the machine is the state it is in and the input. And typically we would indicate where it is in the input by just a pointer saying what position it is in the input. And the important thing to know about input for finite automata is that the input pointer always advances. So or it only advances. So when we read a character of input, the input pointer moves to the right and it never moves back. All right, so from state A, we have a rule. We can see that we're in state A. The next input character is a 1, and that allows us to take a transition to state B. And so now we're in state B, and where's our input pointer? Well, it's beyond the end of the input, indicating we are at the end of the input. And so now this is, we are in an accepting state, and we're past the end of the input, and so we accept. Okay, so let's do another execution. So we start in state A, and let's take as our input the string 0. Okay, and I'd like to draw the pointer, actually, I should have drawn it before the input. So we'll always put the pointer between two input elements. In this case, and it's immediately to the left of the one we're about to read. So in this case, we're about to read 0. So we're in state A, our input is 0. We look at our machine. We see that there is no transition on 0. All right, and so the machine stays stuck. It doesn't make any move at all. And this is our final configuration. And we can see that we're not at the end of the input, and so this is a reject. Okay, so in this case, the machine rejects that string as not being in the language of the machine. Let's do one more example. Let's say that we're in state, well, we're always beginning in state A, in the start state. And let's say our input this time is the string 10. Okay, and our input pointer is there. All right. So again, we're in state A. The input is a 1, and so we'll move to state B. And now the input doesn't change, just the input pointer changes, but I'll just copy the input over to show the difference. So now the input pointer has advanced because we've read one character of input, and now we're in another state. And now we can see that we're in state B. Our next input is 0, and there is no transition on 0 from state B. And so even though we're in an accepting state, B is a final state, is one of the accept states, we haven't consumed the entire input. And so the machine also rejects this string. So this is also a reject. And in general, we could talk about the language of a finite automata that is equal to the set of accepted strings. Okay, so the language of a finite automaton, when I talk about the language of a finite automaton, I mean the set of strings that the automaton accepts. So now let's do a more complex example. Let's try to write out an automaton that accepts any number of 1s followed by a single 0. So once again, we'll need a start state, and we'll also need a final state. And now let's start by thinking about what the shortest string is that's in the language of this machine. So in this case, we know it has to end in a single 0. So a 0 definitely has to be, a 0 transition has to be the last move. And before that 0 can come any number of 1s. And in particular, there could be no 1s. So one transition in this machine is that from the start state, on input 0, we can definitely go to the final state because the string consisting of a single 0 is in the language of this machine. And now the only question is, how do we encode the fact that any number of 1s can precede this 0? Well, there's an easy way to do that. We can just add a self loop on the start state. and take that transition if we read a 1. And what does this mean? This means that we'll stay in the start state as long as we're reading 1s, and then as soon as we read a 0, we'll move to the final state, because that has to be the end of the string if the machine is going to accept it. So now let's do a couple of examples to convince ourselves that this works. Let me label these states again. So this is state A, and that's state B. So let's write out here state and input. So we'll begin in state A, and let's take as input 1, 1, 0. Okay, so let's do an accepting case first. All right, so our input pointer begins to the left of the first character. So we're in state A, in start state. We're reading a 1, and that says we should take a transition that puts us back in state A. And so we advance the input pointer. Okay, now we've consumed the first 1. And again, we're in state A, and the next input is a 1, so we'll make another transition to state A. And the input pointer will advance. Okay, so now we're in state A, and the next input is a 0, and so we'll take the transition to B. And now we're in this configuration, so the input pointer has reached the end of the input. We're in an accepting state, and so the machine accepts. 110 is in the language of this machine. So now let's do an example where we will reject the input. And what configuration do we begin in? And again, a configuration for a finite automaton, that just means a point in the execution, and it always consists of a state and a position of the input pointer. So our initial state is A, and now let's just choose the string, I don't know, let's take 1, 0, 0. And let's confirm that this is not in the language of the machine. All right, so we begin in state A, and our input pointer is there. Now we read a 1, and that means so it's from state A on a transition of 1, we stay in state A, and the input pointer advances. And now we see a 0, so from state A on input 0, we make a transition to state B. And now the input pointer is here, so now we're in state B, and we have an input of 0, but there is no transition out of B on 0. There are no transitions out of B at all. And so the machine gets stuck. It can't get to the end of the input. And again, even though we're in an accepting state, we haven't read the entire input yet. And so that means the machine will reject. And so 100 is not in the language of this machine. Up to this point, a finite automaton consumes a character of input every time it makes a move. So if it can make any move at all, the input pointer advances. Now we're going to talk about a new kind of move, the epsilon move. And the idea behind epsilon moves is that the machine can make a state transition without consuming input. So for example, if I have my state, and I'm in state A, and my input, and let's just say that we have x1, x2, x3, and for some reason we're about to read x2. When we make an epsilon move, the machine changes state, but the input pointer stays in exactly the same place. So the new configuration of the machine would be that we're in state B, but our input pointer is still waiting to read x2. So you can think of an epsilon move as a kind of free move for the machine. It can move to a different state without consuming any input. And just to be clear here, the machine does not have to make the epsilon move. It's a choice. So we can decide whether to make the epsilon move or not. Now, epsilon moves are the first time we've mentioned the possibility that a finite automaton might have a choice in what moves it makes. And there's actually an important distinction between automata that have choices and those that don't. So deterministic finite automata have two properties. First of all, they have no epsilon moves, so they must always consume input. And second, they only have one transition per input per state. What do I mean by that? That means that if I look at any state in a deterministic automaton, they can never have something like this, where they have two possible moves for the same input. All the outgoing edges in a deterministic automaton must have different input labels. And then non-deterministic finite automata are just those that are not deterministic. So in particular, a non-deterministic automaton can have epsilon moves, so it can choose to move to another state without consuming input. And they can also have multiple transitions for one input in a given state. So something like this is okay for a non-deterministic automaton. Now let me just point out that really epsilon moves are enough to create non-deterministic automata, and that this second case where you have multiple transitions on the same input can be simulated just by a slightly more complicated machine with epsilon moves. So for example, I can draw this machine in the following way. I can simulate the machine that's circled there in the following way. I can have a state with two epsilon moves, and then each of those states has a move on A. So if I were to label these states 1, 2, and 3, then this would be the state that corresponds to 1, and this would be the state that corresponds to 2, and this would be the state that corresponds to 3. So anytime that we have multiple moves out of a state on a single input, we could always replace that by a few more states with epsilon moves and have every state in the machine only have a single transition for every possible input. So really the only fundamental difference between deterministic automata and non-deterministic automata is whether they have epsilon moves or not. A key property of a deterministic automaton is that it can only take one path through the state graph per input. So this is per input. What do I mean by that? Well, the automaton always begins in the start state, and let's take a very simple input string like ABC. And if we look at the sequence of states that the deterministic automaton will take for that input, this path through the state graph is completely determined by the input because, again, it has no choice. In a given state, there's only going to be one transition labeled A, and it's going to take you to a state that only has one transition labeled B, and that goes to another state that only has one transition labeled C. And so every input determines the path through the state graph that the automaton will take. And this is not true for non-deterministic automata. So it might be, for example, that beginning in the start state and on input A, that there is some state I can go to on that input A, but there may be another transition labeled A that would take me to a different state. So the automaton might be able to go to one of two different states. And again, there might also be epsilon transitions. And so what happens with non-deterministic automata is that in general, as they proceed through the state graph, as they execute on the input, they could wind up in any number of different states. Okay? And the rule with a non-deterministic automaton about when it accepts is that it accepts if any path accepts. So an NFA accepts if some choices lead to an accepting state at the end of the input. That is, the non-deterministic automaton can choose what move to make, and as long as there is some choice it could make, that would get it to an accepting state. So let's say, switching colors here, that this was an accepting state down here, and it took this path, then it would accept. And maybe all these other paths are rejecting paths. That doesn't matter. As long as there is one path, one set of choices the NFA could make to get it to an accepting state at the end of the input, then we say that that string is in the language of the NFA. The fact that NFAs can get into multiple different states depending on the choices they make during a run is important and will actually play a central role in a future video. So we're going to do a quick example here to just make sure that this is clear. So here's a little automaton, and note that it is non-deterministic. From the start state, there are two possible moves on input 0. And what we're going to do is just walk through an execution of this machine on a sample input and see what different states it can get into. So we begin in the start state, and we should probably label our states actually so that we can refer to them. Let's call them A, B, and C. And let's say that the first input is 1. And so what does that mean, that means we'll take this transition, we'll just go from the start state and come back to the start state. And so the set of states that the machine could be in after the first transition is just the set A. So it's guaranteed to still be in the start state. So there's no choices with the first move. Now let's say at the second input character is a 0, and now we do have a choice. We could either go to state B or we could go to state A. And we could think of this then as a set of possibilities that after we execute this move, this transition, the machine could be in any one of a set of states. And actually, this completely characterizes the possibilities for the machine. We've read the second input character, and now we could be in a set of states. Okay, we could be either in state A or in state B. And so now let's say we read another 0. And where could we go then? Well, if we're in state B, we could make the transition to state C. But if we're in state A, then we'll make the transition either to state B or again to state A. So in fact, we could be in any one of the 3 states if we read another 0. Okay? And now I think you can see what the rule is. So at every step, a non-deterministic automaton is in a set of states of the machine. And when it reads another input, we consider all the possible moves it could make to compute the complete set of states it could be in at the next step of the machine. Okay? And then finally, how does we decide whether the machine accepts? Well, we look at the final state after the last bit of input is read, and if there's any, we look at the last set of states after the last input character is read, and if there's any final state in that set, then the machine accepts. And in this case, after we read 0, we see that an accepting state C is in this set of possible states, and what that means is that there was some set of choices that the machine could make that would get it into a final state at the end of the input, and so the machine accepts this input. Okay, so if there's a final state in the final set of possible states, then the non-deterministic machine accepts. It turns out that NFAs and DFAs recognize exactly the same languages, in particular the regular languages. So NFAs, DFAs, and regular expressions all have equivalent power. They can only specify regular languages. DFAs are definitely faster to execute, primarily or entirely because there are no choices to consider. So a DFA can just follow a single path through the state graph, whereas with an NFA, we have to keep track potentially of the set of choices in the NFA, and we might be in a set of states. However, there are some advantages to NFAs. They are in general much smaller than DFAs. In fact, they can be exponentially smaller. So the smallest NFA may be much, much smaller than the smallest equivalent DFA for the same language. And so essentially there's a space-time trade-off between NFAs and DFAs. NFAs might be more compact, but DFAs will be faster to execute.